It's my pleasure to introduce Dr. Vishal Sahni. Dr. Vishal Sahni is Assistant Professor in Faculty of Engineering at the Albag Educational Institute. He obtained Bachelor's degree in Electrical Engineering in 1999, MTech in Engineering Systems in 2001, and PhD in Evolvable Hardware Systems in 2004, all from the Albag Educational Institute. He has been recipient of President's Gold Medal of the Albag Educational Institute twice, in 1999 and 2001. His research interests are quantum and nanocomputing. He has authored a book entitled Quantum Computing, published by McGraw-Hill, and co-authored other two books on nanocomputing and quantum information systems. He is the coordinator of the Memorandum of Understanding between the Albag Educational Institute and University of Waterloo. Dr. Sahni is also the Secretary of the Systems Society of India.
Thank you, Professor Kalra, for the introduction. My talk is on application of graph theoretic quantum system modeling to complex systems. The outline of the talk is, we start with application of graph theoretic quantum system modeling to string theory. We move on to theory of many things, evidence of quantum computing in the brain, and contribution of DEI, quantum nano system center, to the field. String theory is an excellent candidate for a unified theory of all forces of nature. String theory is a quantum theory, and because it includes gravitation, it is a quantum theory of gravity. The lack of adjustable dimensionless parameters is a sign of the uniqueness of string theory. It means that the theory cannot be deformed or changed continuously by changing these parameters. Graph theoretic modeling has been applied to string theory. In special relativity, the speed of light is the same for all inertial observers. In comparing the coordinates of events, two inertial observers called as Lorentz observers find that the appropriate coordinate transformations mix space and time. The events are characterized by the values of 4 coordinates, a time coordinate t, and 3 spatial coordinates x, y, and z. This is the graph representation for basis state vectors. This is the time dimension, and these are the 3 spatial dimensions. If we consider a second Lorentz frame S, let us assume that 2 events are separated by the coordinates x mu and x mu plus delta x mu. We now consider a second Lorentz frame S dash, in which the same 2 events are described by the coordinates x dash mu and x dash mu plus delta x dash mu respectively. In general, not only are the coordinates x mu and x dash mu different, the coordinate differences delta x mu and delta x dash mu are also different. However, the graph representation for x dash mu is similar to the graph representation for x mu. However, the intervals delta s square and delta s dash square defined as follows are the same. Minus delta s square is minus delta x naught square plus delta x1 square plus delta x2 square plus delta x3 square. This is the time dimension term. This has a minus sign. The other 3 are positive. And however, the delta s square term and delta s dash square terms are the same. This is an invariant in both the coordinates. The minus sign is in front of the time term delta x naught square, as compared to the plus sign appearing before the space-like differences delta x1 square, delta x2 square, and delta x3 square. This sign encodes the fundamental difference between time and space coordinates. The minus sign in the delta x naught square term implies that delta s square is greater than 0 for events that are separated in time, or time-like separated events for which delta x naught square is greater than delta x1 square plus delta x2 square plus delta x3 square. This discussion holds true for delta s dash square also. We move on to light cone coordinates. The light cone coordinates x plus and x minus are defined as 2 independent linear combinations of the time coordinate x naught and a chosen spatial coordinate conventionally taken to be as x1. This is done as follows. The light coordinates x plus and x minus are 1 by root 2 coordinate system transformation operator matrix into x naught and x1. The graph representation for the coordinates x naught and x1 on one hand, and the light cone coordinates x plus and x minus on the other hand, are shown in figure 3a and 3b respectively, and the transformation operator function between the two is shown in figure 3c. So this is the x naught, x1 coordinates, these are the light cone coordinates, and this is the coordinate system transformation operator function. Understanding the light cone coordinates. The light cone at the given event is formed by all events that can be connected through light rays with the event as shown. So this is the past light cone, this is the future light cone, this is the hypersurface of the present. When we observe the sky at night, we basically see only the past light cone within the entire space-time. A central concept in special relativity is proper time. Proper time is a Lorentz invariant measure of time. If we consider a moving particle and 2 events along its trajectory, different Lorentz observers record different values for the time interval between the two events. If we now imagine that the moving particle is carrying a clock, the proper time elapsed is the time elapsed between the two events on that clock. By definition, it is an invariant, as all observers of a particular clock must agree on the time elapsed on that clock. Similarly, the differential ds is a Lorentz invariant and can be used to construct new Lorentz vectors from old Lorentz vectors. For example, a velocity 4 vector u mu is obtained by taking the ratio of dx mu and ds. Since dx mu is a Lorentz vector and ds is a Lorentz scalar, the ratio is also a Lorentz vector. So the factor of c is included to give u mu the units of velocity. In physical system theory, all the integrals and derivatives have got the same linear graph representation. So velocity is the derivative of displacement. So we have the same field graph. Thus, with respect to the field graph in figure 1, we can write u mu is c dxm by ds. Similarly, for momentum, in special relativity, there is a basic relationship between the rest mass m of a point particle, its relativistic energy E, and its relativistic momentum P. This relationship with respect to field graph in figure 1 is given as follows. Energy and momentum can be used to define a momentum 4 vector as follows. P mu is P0, P1, P2, P3. The light cone components P plus and P minus of the momentum Lorentz vector are obtained as follows. P plus is 1 by root 2 P0 plus P1 and P minus is 1 by root 2 P0 minus P1. With respect to the input-output field graphs in figure 3a and the output field graph in 3b, we can write the light cone coordinates in terms of P0 and P1. The block diagram representation for this is also shown. These are the coordinates P0 and P1 and these are the light cone coordinates, and we have the same coordinate system momentum transformation operator in between. Lorentz invariance can be used with extra dimensions. If string theory is correct, we must entertain the possibility that space-time has more than 4 dimensions. The number of time dimensions must be kept equal to 1. It seems very difficult, if not altogether impossible, to construct a consistent theory with more than one time dimension. The extra dimensions must therefore be spatial. Lorentz invariance is a concept that admits a very natural generalization to space-times with additional dimensions. This shows a world with one time dimension and 5 spatial dimensions. So x0 is the time dimension and we have got 5 spatial dimensions. We move on to process physics. The dominant modeling methodology of physics is static. We model the universe as a 3 plus 1 dimensional pre-existing structure where time shares a very similar status to that of space, despite our everyday experiences of the two phenomena as being remarkably different. Process physics sprang out of an initial desire to explain from where such a structure could have emerged, that is, to form a pre-geometric model of the universe. Process physics, as described by Christie-Guiteau, has now been formulated as a far more general modeling paradigm that is capable of generating complex emergent behavior. We look at the low-level process physics model. The initial low-level model constructed within the process physics paradigm attempts to work around the static object-driven methodology of reductionism by adopting a more relational approach. This is achieved by starting with a set of nodes for the sake of analysis, but instead of focusing upon the objects themselves, the connections between individual nodes are analyzed. This shows a simple relational structure of nodes, their connections, and the iterative equation. This is the set of nodes, and this is their graph matrix representation. It is assumed that the B matrix representing this system of nodes updates discretely according to the following iterative process. Bij is Bij minus alpha is the tuning parameter, B plus B inverse, and omega is an additive noise term which provides a sense of openness to the system. At each iteration, the action of the noise term leads to the creation of new Bij links incorporating a sense of innovation and contingency into the system. We performed a MATLAB simulation of this iterative equation. A 200 cross 200 B matrix was initialized and its diagonal elements were set to 0. Another 1000 elements in the B matrix were set to small numbers between -0.1 and 0.1 so that anti-symmetry holds. The values for the circuit were entered into the B matrix. This was the initial B matrix called as B initial. In B initial matrix, those elements whose absolute value was above 0.5, a threshold for substantial degree of connectedness, were counted, and these are listed in the table on the next slide. We'll come to that. In all cases, the value is 11 of non-zero elements with absolute value greater than 0.5. In the initial circuit, these are the only connections with substantial connectedness. The iterative equation was applied P is 10, 100, 1000, and 10,000 times with the following steps in the iteration. The inverse of the B matrix was generated. and this term was computed, the additive noise term omega ij was generated randomly within the range minus 0.1 to 0.1 and added to the result in step A. In the final B matrix, B final, the elements whose absolute value was above 0.5, a threshold for substantial degree of connectedness, were again counted, and these are listed here. It can be the value of the alpha tuning parameter was taken as 0.1, and the noise term omega ij was generated randomly as a random number between 0 and 0.1. So we can see that there is a tremendous increase in the number of non-zero elements with absolute value greater than 0.5 in the B final matrix. We move on to theory of many things. In terms of systems modeling, instead of the system scientists and practitioners getting bogged down with similar dreams of modeling theory of everything, one could perhaps look for modeling theory of many things. There is certainly a possibility of founding such a unified modeling theory of many things, not everything, based on linear graph theory and unified field theory, not just quantum or string theory, but perhaps some futuristic M-string theory or whatever that qualifies as the grand unified theory of so-called everything. This modeling theory of many things will then span perhaps all kinds of systems, including natural systems, designed physical systems, designed abstract systems, and human activity systems. Various kinds of systems can give rise to their own peculiar problems, which can be attempted to be resolved to the extent possible. Christie-Kitto has prepared a complexity scale for systems ranging from simple like projectile motion and billiard balls through complicated like weather dynamics, food webs, etc., to complex systems like bound states, quantum tunneling, and so on. So graph theoretic field modeling has been applied for simple systems, complicated systems, but it is at the higher end of complexity scale that the unified quantum field graph theory holds considerable promise and potential for modeling systems successfully. This is the Christie-Kitto scale. So for simple systems, graph theoretic modeling has been applied. For complicated systems also it is being applied. For complex, contextual, and observer-driven systems like quantum field theory, postmodernism, evolution of mind, language, societies, this is where graph theoretic modeling holds considerable promise too. There is evidence of quantum computing in the brain through microtubules. Quantum computers may be much closer to us than previously thought. In fact, there are billions of quantum computers inside our brains. This is one of his figures showing orchestrated objective reduction and simulation of the visual information transfer by using the mechanism of teleportation. Schematic representation of neurons showing the arrangement of microtubules inside that. Of course, I'll skip this, we'll hear more of it in his talk. Each tubulin molecule may switch between two or more conformation or in a quantum superposition of states. And the states collapse to one of the outcome states in the end. We plan to acquire a whole head squid system in a superconducting magnetic shield to study quantum computing in the brain in the twin facilities of the Quantum Nanosystem Center and the Center for Consciousness Studies, which has also been set up at DEI. We are also attempting modeling of microtubules as quantum Hopfield networks, and we have modeled tunneling energy functions and bidirectional Coulombic energy functions to compute the total Hamiltonian or Lyapunov energy function. And there are some more innovative diagrams. I move on to some of the equipment we have at the Quantum Nanosystem Center, DI Research and Technology Park. We have got superconducting quantum interference devices, squid-based quantum computing devices installed in pulse tube coolers, proposed to be utilized as qubits in the back room over there, and its compressor is in the adjoining room. It is the first setup of its kind in India. It will be made available for online use through web interface of the DI Virtual Labs project. We have the pulse tube cooler. This is its schematic. And we have attempted experiments here. We have achieved temperatures of 3.26 Kelvin. This is basically the readout system for a qubit. We are now in the process of acquiring the encoding system also. This shows the state of the field in India compared to the world. This is the yearly number of ARXIV publications, representative of the research work going on in the field. So India is shown in blue, so we still have a long way to go to bridge the gap. China is in the red line. Japan is the green line. The blue line is the contribution of Indian scientists to the number of publications in the field. This shows the funding of quantum information or computation processing and communications, the world scenario. India is somewhere here, so this also needs to catch up. The Quantum and Nano Computing Virtual Center is trying to plug this gap. We are a project under the National Mission on Education through Information and Communication Technology of Ministry of Human Resource Development, Government of India. The partners are Dalbagh Education Institute, IIT Delhi, Professor Kalra is the co-PI from IIT Delhi, IIT Kanpur, Professor Debrat Ghosh, and from IIT Madras, we have Professor Mangal Sundar. The project objectives are to bring together through ICT complementary research strengths of the partnering groups spread all over the country, because the field involves people from various diverse disciplines, to utilize the latest distance learning technologies and provide opportunities to young scientists and researchers, dissemination of knowledge through ICT in quantum nanocomputing, through organization of joint seminars, courses, webcasts, annual winter school on quantum nanocompute later also. This is the roadmap we are trying to follow. We started out by generating awareness in the field. We organized a shared vision workshop on quantum nanocomputing, SQUAN 2007. Back Action 2006 was organized at IIT Kanpur by our partner institute. Then first Indian books on quantum and nanocomputing were co-authored. Our collaborations were strengthened further in the Quantum Nanocomputing Conclave 2007. The first Quantum Nano School Kansas 2008 to promote education in this area was organized in December 2008. Then in the pilot stage of the project, we organized Kansas 2009. We had Nobel laureates also, and our pool of partner institutes was also expanded. Then in Kansas 2010, we attempted unification of interdisciplinary focus areas of partners for wider catchment, and our realization is ultimate qubit demonstration and realization of an Indian quantum computer. Our national partners, of course, IIT Kanpur, Delhi and Madras are our partner institutes, but we are also collaborating with IIC Bangalore, IIT Bombay, Kharagpur, TIFR, IMSC Chennai, IOP Bhubaneswar, ISI Kolkata, IIT Roorkee and BARC Mumbai. Our international partners are Institute for Quantum Computing, University of Waterloo, Canada, Institute for Quantum Sciences, Michigan State, MIT, University of Maryland, College Park, IBM Watson Research Center, and Alcatel-Lucent Bell Labs. We are trying to develop a roadmap for quantum information computation. So our short-term goals are deliver SQUID-based quantum computing device prototypes, have a web-based interface for using these devices at the national hub from remote locations, and have a conceptual framework for remote communication using quantum teleportation. Then in 5 years, we have got an ambitious goal of developing tools for unified representation in quantum information computation, quantum field theory and string theory. And in the long term, we plan to have unification attempts for theory of many things. We have regular classroom interaction between DEI, IIT Kanpur, University of Waterloo and Michigan State University. In fact, this is the first workshop we organized, soft quantum and nanocomputing in 2007. Then we had the Quantum Nanocomputing Conclave in 2007. The first Quantum Nano School was organized in December 2008. Then it was attended by over 100 students and researchers from all over the country, and all lectures have been put up online on the project website for Kansas 2009 also. There was a panel discussion at Kansas 2009 which concluded that critical mass is being approached in India in the field with experts from physics, chemistry, electrical and electronics engineering, computer science and information technology, and they appreciated that the Quantum Nano Center is acting as a glue or catalyst for promoting this field in the country. There was international review of the quantum roadmap during Kansas 2010, and the consensus was that the project has brought together through ICT the research groups of the country, and it should continue further, and there should be continued dissemination of knowledge through ICT in quantum nanocomputing to industries and R&D institutes, and a few working models, demonstrations of experiments in the field should be set up at a few labs in India so that first-hand experience is available to young learners in the field in the country itself. We have co-authored books at DEI and IIT Kanpur in the field. DEI and University of Waterloo people have together we have co-authored books in the field. I quote from Love Grover. Love Grover was here at SQUAN 2007. He said that having missed the boat in the Silicon Revolution in the 70s and 80s, India should make every attempt not to let it happen again, even if it means spending some resources on technologies like quantum computing, which are speculative but hold tremendous potential. United States has its quantum information science and technology roadmap. Europe has its quantum information processing and communication strategic pan-European effort to position Europe as a world leader in quantum information processing and communication. Canada has its Quantum Works, an NSERC funded innovation platform. Institute for Quantum Computing, Perimeter Institute, they are all partners in that. So we plan to have a similar consensus in India and develop a roadmap and work for the development of the field in India. The speaker is extremely grateful to revered Professor Prem Saran Satsangi Saab, Chairman Advisory Committee on Education, Dalbagh Educational Institutions, for introducing him to the fields and paternal guidance and incessant encouragement.
Questions? With regards to your simulation, where
Right.
you are trying to
Right.
have this iterative method,
Right.
So it also demonstrates potential for parallelism, I believe.
Right.
So are you trying to?
In fact, we are trying to model quantum Hopfield networks in the brain as quantum microtubules in the brain as quantum Hopfield networks. So we have taken a quantum Hopfield network and we have tried to model it for 10 neurons, 100 neurons, 1000 neurons, 5000 neurons. On my desktop, I could go to 5000 neurons. Then we have a cluster on which it ran up to 1 lakh neurons. Presently, we are trying to model 1 million neurons in the brain. So, but that has still have to be vectorized and run on a cluster.